Okay, so the question was this: which one spins and which just the ground? So if you're at home right now and you guess the hollow disk and the solid disk, you are wrong. Right? The correct answer is the solid sphere, but do not worry, you are not alone in guessing it wrong. If you are right, I congratulate you. Um, right, but how did we arrive at this? Come, let's look at some of the interesting ones at home. This is a simulation, right? How did they get this simulation? Ah, you see that the hollow disk, right, has a larger moment of inertia. It's in fact the hollow disk is in fact has a moment of inertia m r squared. Okay, stop. What happened? Okay. Right. So your hollow sphere has a angular moment of inertia, uh, rotational moment of mr squared. Your solid disk have a rotational moment of inertia. How much? I don't memorize it. I'm sorry. Half mr squared. And the sphere has a rotation moment 2 over 5 mr squared, which is the smallest of them all. Right? But even if you do not have the exact numbers, you should be able to guess, because the moment of inertia I is given by r squared dm integral. So the further away most of your mass are, the larger the moment of inertia. Right? No? Yes? No? Yes? Yes? So this has the largest moment of inertia. It should accelerate in its spinning. The angular acceleration should be the slowest. So Tiedong's answer is perfectly logical. Using t tau equals to I alpha, you should arrive at the conclusion that this will be the fastest, followed by the full disk. Sorry, where the sphere will be the fastest, followed by the full disk, followed by the hollow disk. Okay. But let's look at a complete discussion of the energy. Right? You can go to Courant again. Right? If you have, the question was, if you have a hollow cylinder, a solid cylinder, and a sphere, exactly the same. Why? The students who are attending this university course, probably went online and asked someone to help them solve for their homework. Unfortunately, it works that way. Right? And engineers being nice and PhD students being nice will try to answer. But anyway, the point is this. The total energy, he uses a total energy equation as mgh plus half mv squared translation energy plus rotation energy. Perfectly cool. But here we could actually use a conversion to the loss in mgh will become half mv squared plus I omega squared. And you realize that the bigger the I, the smaller that v and omega must be, because omega is essentially just v squared over 2r. Right? So if your I is the largest, your v has to be smaller when you reach the bottom. Hence, you must take the longest time. Okay? So this is a more complete, in-depth discussion, which even allows you to find the velocity of the object at the bottom of the slope, should you want to. Okay? Can? Right. We have 2 more minutes. But just let's look at this slide. Okay. When the cylinder rotates through an angle of theta, its center of mass moves a linear distance r, s equals r theta. The velocity of center of mass is ds d theta. Right. So when it rotates, the center moves through this distance. This line of the movement of center of mass is equal to this distance moved on the surface. So the velocity of center of mass is given by ds theta, which is given equals to all this, r omega. Acceleration would then equals to r alpha. Okay. So all points on the cylinder have the same angular speed, different linear velocity. The linear velocity of any point is in a direction perpendicular to the line from that point to the contact point P. Okay. Like this. At any instant, the part of the rim that is at point P is at rest relatively to the surface, right? Because we are assuming no slipping. If you have slippage, that is even more difficult thing to talk about. Here, I don't think you can see it very clearly, but what we do is that we mark one point on the object, right? So this is the object, this is the maximum height, mark 1 point, and we follow that 1 point as it circles. It actually does this. So let's say I mark point P, and I rotate it. You actually do something like this, point, like as if it's bouncing, but it's not. It's rotating. Okay, moving on. All right, I will stop after this slide and the next one, okay? So rolling motion with center of mass moving at velocity, right, is equals to pure translation with speed VCM plus pure rotation with omega equals to V over R. The V equals R omega, so omega is V over R. Right, so this is it. A rolling motion. Right, this is the last slide I will leave you at. You can read the rest, which will give you a better understanding of everything else. But we will stop here for today. The rolling motion, which is what we are discussing now, is a combination of sliding motion plus the rotation motion. So you see that the vector at the top, the object moving at the top, has the longest speed. In fact, it's the addition of this plus this. This is something again that this whole chapter will not be discussed in your H2, right? So it makes sense for you to revisit this video, even if you're in this lecture hall. Okay. Right, so that's it. Next time we'll meet again. Last time that I'll see you. Right. After this will be next week. It will be Mr. Wong, then Dr. Goh, who will rotate and teach you other interesting topics for Olympia. Okay. Right, that's it. Thank you and have a nice day.